I have a really fun project today. We are going to do a quick DIY build of this 280 amp hour 12 volt lithium iron phosphate battery with a 200 amp JK BMS. Then we'll look at the capacity and performance characteristics and compare those to some off-the-shelf options. Is it really worth building a DIY battery? Well, let's see. Welcome back to Projects with Everyday Dave. Let's build it. All right, the first thing we're going to do is assemble the JK BMS. The one I'm using for this build has all the bells and whistles. It's the JK 200 amp BMS. It has Bluetooth, CAN bus, temperature sensors, and heating. If you want to save a little cash, you could always get a BMS with fewer features. But when I go DIY, I'm targeting getting the best specs for a lot less money. There's really no positive wires for the BMS connection. They're all negative, and I have a couple of red cables, so I'm just going to wrap them in black tape so there's no confusion. There we go. Cables to the battery, cables to the inverter. We're going to be using 4 lithium cells, and based on our diagram, we'll need the negative, the first one on here, and then we'll need one for each battery. 1, 2, 3, 4 wires. 1, 2, 3, 4. And then the very last one is the positive connection, so that's 5. So I can put ring terminals on all of those. I like to use heat shrink terminals. I just got these off of Amazon. I'll leave the link in the description. So I just need 5 of those for 16 to 22 gauge. There isn't quite enough exposed conductor there, so I'm going to expand those just a little bit. It's easier if you set it in the tool first, and then you can put the wire in. Make sure the insulation doesn't go past the crimp ring. So the rest of these we can just put out of the way. I'm going to put a little piece of tape over the end of them just to make sure it doesn't contact something it shouldn't and cause a problem. All right, this main cable plugs into the main bus. Our temperature sensors plug into the far end, and our on-off switch plugs into this one here in the middle. There we go. Main cable, on-off switch, temperature sensors. Now we have our battery negative and then our inverter negative. These cables I'm using are slightly undersized at 25 square millimeters. I want the equivalent of a 2-aught cable. And using the wire size calculator, I can see that it's actually 67 square millimeters for 2 of these. In order to achieve my target, I could replace them with 2 2-gauge cables, and by recalculating, you can see that is almost exactly equivalent to a 2-aught cable. Since these are really short, I'm not going to worry about it for this test, but for a 200 amp BMS, I recommend using 2 2-gauge cables for this connection. Now I need to torque these down to the specified torque using a torque wrench. Just set my torque screwdriver to 8 Newton meters. There we go. And torque these down. Which seems like a lot, but they've got to be tight. All right. Main setup is done. It's time to connect up our battery. Ever since I made a video with a DIY 48 volt battery system, there were a lot of complaints that it was hard to get the batteries and the battery prices were fluctuating. So I've been trying to find a good, reliable source for batteries. And this vendor says they can support things. They can give a discount to my viewers. So it should be a good price and hopefully a quality battery. So today we're going to confirm whether or not these batteries are high performing, and then I'll be able to recommend them. So they're packed with insulators, really nice thick foam, and first glance these cells look really nice. They are smooth and beautifully welded. They are very flat. Nice. Well, let's hope they work as well as they look. So each box comes with 2 cells, and it also has some hardware. We have bus bars, and they are not the flexible type. They're solid bars, so you may want to order different bars that have the flex part in the middle. And then they have lock nuts that come with them. So everything you need to put the battery together. All right, let's build it and give it a test. These are EVE 280 amp hour cells, and I'll be able to get 300 plus amp hour cells as well. There'll be multiple options. 3.2 volts, these are the dimensions. The barcodes are visible and easy to read. Everything looks very clean and new. To put the battery together, we'll place the cells in alternating positions. So plus, minus, plus, minus. Then I can drop my insulators in between the cells. I've created 2 blocks so I can compress the cells. Ideally, I would use something non-flammable such as aluminum plate, but I only had wood on hand at the moment. I'll just use some non-conductive Kapton tape to hold everything in place. Just that tape holds surprisingly well. And people often ask, is it necessary to apply pressure or not? And the reality is, no, you don't have to. The cells will operate without that, and they have natural expansion and contraction that happens as they charge and discharge. But the pressure on the cells helps reduce mechanical failure, reduces dendrite growth, and will increase the life of the batteries. I've made my boards just a little bit wider than my cells so that I'll have space to put my tensioner in there without damaging the cells. I don't want to nick through to the metal casing. In fact, I might put a little spacer to protect my batteries. And then I have some strapping. This is from a package that I received. I saved the strapping because I like to reuse things, not because it's practical or makes any sense. I don't have an exact calibration for tension. I just tightened it enough to start crushing the edges of the boards. I'm sure there's a more exact science to it, but that's what I'm going with here. There we go. Oh man, that is not light. We are ready to go. Could play a song. Probably the safest thing to do would be to use some double-sided tape to attach this if you wanted to attach it directly to the battery. I am actually going to use screws, and I don't really want to recommend that, but if you were, you want to make sure that they don't go into the battery. Now, I'm making sure that these are nowhere near long enough to go into the battery. If you were to shoot a screw into the battery, you're looking at a big fire. So yeah, do not drive a screw into the battery. All right, now that's securely mounted. I'm going to disconnect my balance leads because I want to confirm they're all connected properly before we run anything. Now, as we start connecting things up, make sure you don't have any jewelry on, wedding rings or anything like that. We don't want to accidentally touch across the terminals, especially once we start getting these built up. There's a tremendous amount of current available, and we don't have all the protection systems connected. Now, we're going to connect these cells in series. So our main negative will be here and our main positive here. This is the battery end connection for the BMS, so that'll connect to this post. That'll make this my negative output and this my positive output. So I'm just going to leave our post protectors on these for now. I prefer flexible bars. The ones that come with these batteries are rigid, so I'd recommend that you buy other bars that have a flexible middle. Batteries do expand and contract even with the bands on them, and that expansion and contraction will over time reduce the torque on the bolt to joint. So this is not the ideal bar, but it'll work for our demonstration anyway. All right, so we'll make the battery starts negative to positive, then positive to negative. And that goes for this battery, then positive to negative, and then positive to negative makes those end to end. Now, in addition to that, we need to put all of our BMS sensors. Now, I've disconnected this from the BMS so that we can make all of our connections and make sure that it's correct before I plug it in. So I'll start with the negative wire, and that will go to the negative post. I'm going to put a nut on there temporarily so that I can make sure that everything's working before we torque it all down. Now, if you just think of it in terms of checking the voltage across each cell. To check the voltage across this cell, we'll need the negative and the first positive. First positive would go on this one. Now, if I want to check the voltage across this cell, I already have a connection at the negative side, so I want to go to the positive 2. So that would be this one. Now, I know the voltage of 1 and 2. Now to check the voltage of 3, I already have the negative side from here. So I only need the positive side of this one. And then for the final battery, I want the voltage from negative to positive. I have the negative, so I put this guy on the positive. And we need the final positive, which is the far outer pin. So there's actually 2 on this post. All right, now I can just temporarily snug these up. We can check the voltages on everything and make sure it's correct before we turn anything on. When you're tightening things, make sure you don't get any insulation under the nut. All right, now that I have everything snugged up, I can check the voltage of the pack and all of the individual wires before I plug anything in. So the main pack should be around 13 volts. 13.2, so that connection's good. And then each cell should be around 13.3 volts. There we go, 13.29. Now I want to check that my balance lead wiring is correct before I plug anything into the BMS. To do that, I'm going to check the voltage between each cell on my plug. I'll put the black probe on the first black negative wire, and then I'll connect to the cell 1, and I should get 3.28, and there we are. Then I'll move my way down, and I should get 3.2 on each one, and none of them should be negative. 3.3, 3.3. So now I know that I have correctly wired those. I can go all the way across the whole pack with the negative at the first hole and the positive at the other end. That should be the whole pack, 13.2 volts. And that should also be the same as the number 4 pin, 13.2 volts. Okay, now I know this is wired correctly. I can plug it into the BMS, but before I do that, I want to torque all of them down. I put some tape on the other end so I don't accidentally connect something I don't want to. And now I want to connect the negative battery connection point, which on our BMS is the B minus. We want to make sure that battery for B and minus for negative terminal. So that's this cable. Now when I put it on, I want to make sure that I don't have any insulation under the contacts. Now I can push this, I got a little bit of tape up there and push that back. I don't want, make sure that nothing gets between the contact surfaces. Now we'll put these on in such a way, and one coming this way, and my sensor, final nut. Now I can torque all of that down. When I get to the point where I have the possibility of touching something that I don't want to, I like to add just a little bit of rubber insulation. This is only 12 volts, so we're not working with super high voltage here, but just a little added protection. Now I can torque these down, and I'm going to torque them down to 8 Newton meters. Set that, I have 8 Newton meters. Okay, that's good. Now I can work my way around. For the positive terminal, I'm going to add a 250 amp fuse that mounts right to the post. So we'll go ahead and put that on. This guy, then I can put these 2 leads on. I'm going to torque that to 8 Newton meters. Okay, now we have our positive post. Now I can torque down all of the other points. Okie dokie. Now I can plug in my BMS. All right, well, we should be able to power it on now. There we go. Power's on. See if we have anything on the output. Here I should have my 14 volts. 13.2, and then this should not be putting anything out yet. No. All right, so now we just need to connect by Bluetooth, but first let's finish our wiring. Turn that off. Boom, nice. Okay, let's clean this up. All right, I have 2 temperature sensors I want to place. Temperature sensors go in the final port here, and I'm going to slide them under a bunch of stuff. I'm going to put one behind this. No, I can tape it on there. There we go. And I will put the other one on this side. Run it behind this Kapton tape. Right there. All right, now I'm going to use some twist ties and zip ties to clean up the wiring a little bit. All right, there we go. Now, just to give ourselves some additional protection, if something were to drop on this, I don't want to touch across these terminals. I have my final output with a cap on it, but the backside could be touched, and so could any one of these others. So I like to put a little Kapton tape across things, just for good measure. May not be the most beautiful looking, but all right, not super pretty, but makes me happy. Now, of course, ideally you'd put this in some kind of case, but you can use whatever case you want. We're not going into that today. Positive post, my negative post, and a power switch. Now I'm ready to fire up the BMS and get the software settings set up. Then we can run our tests. With all the wiring connected and our BMS turned on, you hear a little beep. Then you can go to your phone, download the JKBMS app, and start it up. The Bluetooth connection should find your BMS. It beeps, recognizing it's there. Put in the password 1234, which is the password for pairing. Not to be confused with 123456, which is the password for changing the BMS settings. All right, now we're in. We can see the cells. Cell 1, 2, 3, and 4. The lowest one is cell 1, but they're all almost exactly the same. And I have a warning: cell count is not equal to settings, modify. So we need to make some changes in our settings. You can see right now charge, discharge, and balance are all off. So we'll go to the settings, and our cell count is 4. All right, so password for changing setting is 123456, and you're going to want to change that. And we have lithium iron phosphate, and I can select that now, but I never want to hit that again because all my settings will change. Our cell count is 4, and the capacity for these particular cells is 280 amp hour. And I'm going to set my balance voltage just a little bit more precise to 5 millivolts. Now, calibrating voltage is if the BMS is sensing something different than the actual output. In our case, 13.15, and we have 13.15, so that's pretty much right on. Right now, we're not going to change the current because we don't know if it's off. Then you can click on Advanced Settings. I'm not going to go through every one of these. There are some other videos I'll link to in the description. Off-Grid Garage goes into great detail on these settings. These are the ones I've decided to go with. You can leave your argument for why you do the ones you do in the description, and let people judge. Okay, I just have a simple power management board set up here. This side connects to the battery. I have my plus and minus cables, and all of the main cables are 2 watt. I have a Victron shunt, so I have power in from the battery and out on the other side of the shunt to the negative bus bar. The shunt is connected to this little display so that I can monitor things real time. The positive for that is connected to the battery terminal side of my on-off switch. This on-off switch will disconnect power to and from the battery, and the fuse is mounted on the battery itself, so I don't have any fuses or breakers on this panel. I do, however, have a small charging circuit, and I'm using a light bulb instead of a resistor to make sure I don't have any short circuits, and it gives me a good visual of when the capacitors are charged. So I'll be able to press this button, the light will come on, and when it dims, I know that the capacitors are charged, then I can turn my switch on. I have the shunt resistor connecting across the poles of the switch. So on the back side, I have one side of the shunt resistor on one side of the switch and the other side of the shunt resistor coming into the other side of the switch. And then this is power to the Victron shunt. So there's 2 extra wires coming to the battery side and 1 wire going to the load side. And that's the way the switch is wired. Here's my special box to replace the charge resistor. And I just use a little light bulb and a button. I 3D printed that. I'll leave a link in the description. You can download that for free. I just used a little light bulb socket and a button. So the way it works is I've connected positive to the hot side of the switch, and negative goes to the load side of the switch. And then I'm just completing the circuit through the light bulb. If I have a short circuit, the light bulb will come on and it won't turn off. If it's wired properly, when I push the button, the light will come on and then dim as the resistors charge, and that will indicate I can turn this whole system on and we'll be good to go. From the switch, the positive goes to the positive bus bar. Now I have my positive and negative bus bars. I have an Anderson connector for my input. I should probably have a fuse on that, but I'm just using a regular charger right now. I could connect my solar charge controller through this Anderson plug. Either way, I should have a breaker in here. Maybe I'll add that later. Then off of these bus bars, I have my cables going to the inverter, and so I can run any inverter I want on this side and any battery I want on that side. Okay, the BMS is on. You can see that with the light there. The Victron monitoring, the Victron shunt monitor is showing 13.17 volts. We have everything set up in the app. I've connected a 14-volt charger to our bus bar here. I taped over the ends of these since I don't have a inverter connected right now. We wouldn't want these to touch. We'd have a major short on our hands. So the charger won't charge until I turn the switch on, but since the monitor is connected to the battery side of the switch, it shows as long as the BMS is on. So let's go ahead and power that up. And then as soon as I turn on this switch, there we go, it sees the battery. Start putting current in, it's putting in 38 amps. Voltage is starting to go up. So I'll let that charge up until it's at 100%, and then we'll cycle it and see what the capacity is. All right, I have everything connected. I'm using this heavy-duty aluminum bracket as a bus bar to make it easier to connect my dual cables to the smart shunt. Since I have Bluetooth on the JK BMS, I don't really need the shunt, but I'm going to use it to compare what the BMS is telling me versus what I've already known to be true using the shunt. Of course, there'll be some differences because of resistance in the wires, but it's just a nice check. The positive is connected to the positive terminal through the post-mounted 250 amp fuse. And then I mounted the BMS on-off switch here to the edge of the battery just to make it easier to access. For this test, I'm using the Boujar V 2000 watt inverter, mainly because it has an app and it'll be really easy for you to see the actual output of the inverter. By the way, Boujar V is offering my viewers 40% off of this inverter for a few more days. And I just posted a video comparing 7 different 2000 watt inverters, so be sure and watch that video before you decide which inverter to buy. First, let's power on the BMS. Hit the button. Beep lets me know it's on and running. And my meter is showing 13.1 volts, so I know everything is operational. Now, before I turn the power on to the inverter, I want to use my pre-charge circuit to charge the capacitor in the inverter. When the light dims, I know we're good, and I can turn it on. Now I have power to the inverter, and I can turn that on as well. Now I can put the output of both of these up here on the screen. Now on the screen you can see I am pulling 0 amps and putting out 0 watts. The first thing I'm going to do is add my 2000 watt water heater that I have on an extension cord here. Will put us really close to the limit of both of these units. So I'm putting out almost 1800 watts and I'm pulling 180 amps from the battery. Now that's within spec for both units. They should be able to run continuously at that level, and I've actually run them for hours. They can do it, it's no problem. The question is, when we push it up over the edge, what happens? So I'll add a few hundred more watts with this light. There we go. Over 2000 watts. We're pulling over 2000 watts. Let's see which one gives up first. This is over its capacity, over 200 amps. This one's over its capacity, over 2000 watts. And you can see how good of a match a 2000 watt inverter and a 200 amp BMS are. They both max out at about the same point. I don't know how long this is going to take. We'll put up on the screen here how many minutes it took when it finally gave up. We're pulling 2.45 kilowatts from the battery. There's some inefficiency there, so the battery always has to put out more than the inverter is delivering. You can also see there's some voltage drop between the battery and the inverter. The battery is saying, I have 12 volts available. By the time it gets to the inverter, it's down to 10.9 volts. And we have some losses through the different connections and the length of the cables. That's one of the problems with 12-volt systems. It starts at such a low voltage, it's really hard to maintain the input to your inverter. If at all possible, you should always go with a 48-volt system. Hey, all right. We finally had one give up. The inverter. The inverter gave up before the battery. I almost gave up waiting for it though. That's a win for the battery. Put over 200 amps continuously. Well, now I don't know how long it could do that, but more than 5 minutes. So that's great. That's fantastic. I mean, it's only rated for 200 amps, and we pulled more than that for a continuous amount of time. Pretty happy with that performance. But now I have to see what its actual limit is. So we're going to try a few other things. I want to run. Eh, hey, it recovered while I was talking. I unplugged the light so it could keep going. All right, let's try some surge loads. Shop vac, 5 horsepower. All right, that was no problem. Let's try the compressor. Nice, some decent surge loads there, no problem. So we tried max performance, some surge loads. If you want to see what this inverter and all 7 of the inverters I tested can do, check out my entire video. I do more than just these. I do all kinds of tests until I hit the limit of the performance for each inverter. I threw the SunGold Power 2000 watt inverter on the bench to see if I can overload the BMS, since it can run longer under overload conditions. I'm adding the 1800 watt water heater, the halogen lamp, and the hair blow dryer on low. That'll push us to about 110, 114% of the 2000 watt inverter's load. And we'll see if it's enough to overload the BMS. Heater. Heater's pushing us near 200 amps. 220 amps. And hair blow dryer. Almost 260 amps. Coming down a little, but 250 plus amps. Let's see how long it can run. Ooh, this thing's going on forever. Well, the inverter won that one. The BMS shut down after almost exactly 5 minutes. The BMS temperature went from about 16.8 degrees Celsius to 62 degrees Fahrenheit at the start of the test to 57.8 degrees Celsius or 136 degrees Fahrenheit 5 minutes later. And it was almost exactly 5 minutes later. And it's not the temperature that shut it off because the temperature threshold's a little bit higher than that. Even so, that is really impressive. I did manage to deliver a surge load of 300 amps. Altogether, I think that's great performance. I don't think you would want anything less than a 200 amp BMS, but this definitely delivers everything that you would need if you're doing a 2000 watt inverter. Now, if you're going to use a SunGold Power inverter or a Victron inverter with a low frequency transformer built in, those can handle a lot higher surge loads and a lot higher continuous loads. You might want more than a 200 amp BMS for that. Finally, I am pretty impressed with this setup. I mean, it delivers really well, and you can fine tune every detail about it. I mean, there's some advantages to building something yourself. If I have a problem, I can address each individual cell. I can modify every single setting on the BMS if I want to tweak something just slightly, the charge voltage or the discharge voltage for my batteries. There's just so much flexibility with it. But is it really worth it? Let's take a look at the numbers. This is the cost breakdown for the DIY version. You need a BMS, battery cables, and a fuse. The difference in price is the 280 amp hour cells versus the 314 amp hour cells. Everything else is the same. I've put together a simple comparison chart to give you some perspective on the option. They are sorted by cost per kilowatt hour, and right away you can see the lowest cost DIY option is about half the cost of the high-end off-the-shelf option. But there are always trade-offs. So let's go through some of the pros and cons. The first 2 batteries on the chart are a 314 amp hour version and a 280 amp hour version of my DIY battery, using the same 200 amp JK BMS. Then I added a 2P version of the 280 amp hour battery, so 8 cells instead of 4, which doubles the capacity, but it's a little bit cheaper because it's still using one BMS and one set of cables. By doubling the number of cells, it exactly matches the LitTime 560 amp hour beast that I used for my 2000 watt inverter testing. This is the highest capacity single cell battery that I know of. The price shown here is the current sale price, and our DIY battery is still $566 cheaper. Finally, the very popular high feature content EG4LL 400 amp hour server rack battery rounds out our comparison. If a 200 amp output isn't enough and you need more power, you could build two 4 kilowatt hour DIY batteries and put them together in parallel. That would give you 8 kilowatt hours of capacity and 400 amps of power delivery. And it would still be under the cost of one EG4LL 5.1 kilowatt hour battery. The cells for the DIY battery are EVE cells, and I ran a capacity test on the full pack to confirm their performance. They performed over the rating by 105%, which is what I would expect from authentic cells. It's very similar to the performance I got with the LitTime 560 amp hour battery capacity test. I didn't have an EG4 battery here to check, but I think you can have confidence in those cells and they will likely perform exactly the same. If you're pairing the battery with a 2000 watt inverter like the BougeRV or the Renogy, which is a very popular inverter, then a 200 amp BMS should meet your needs just fine. If you're using a more robust inverter like the SunGold Power with a low frequency transformer or the Victron 3 kVA or even a 3000 watt inverter, then you probably want to use a 400 amp BMS, which would require putting two cells together. There are some BMS units out there that put out 300 amps, but that's really not going to be enough for some of these larger inverters. I'd go for 400 amps. If you watched my video where I broke down 7 2000 watt inverters, then you saw that the 250 amp BMS on the 560 amp hour LitTime battery was able to support surges upwards of 450 amps. So if you want some margin but don't want to pair multiple batteries together, the 560 amp hour battery is a pretty good option. The DIY version is the only one with active balancing if you believe in the value of that as a feature. The LitTime batteries listed in this chart don't have Bluetooth, but they do have versions that come with Bluetooth for a little bit more money. The DIY battery we built does have an on-off switch, and if you wanted a breaker, you could add one for not a whole lot of extra cost. Only the EG4 battery has a built-in breaker, and the EG4 is also the only one that comes with a screen and a 10-year warranty. The LitTime batteries have a 5-year warranty, and while the individual components for our DIY version do have warranties, for all intents and purposes, there's really no warranty when you build it yourself. Also, you may want some kind of case. If this is going to be sitting on a shelf somewhere, you want to protect it from possible damage or contact. You certainly wouldn't want something to accidentally contact the posts. So which one is right for you? Well, it all depends on what's important to you. If your time isn't worth very much and you're looking for the lowest possible cost, or you just love the challenge of building something yourself and laugh at the risk of fire or electrocution, hey, go DIY. For everyone else, there's a pre-built option out there for every possible application. And with the discounts I provided, you can save yourself a lot of money and help out the channel. If you want to buy these cells, I have a special discount set up with a vendor that has stock in the US, so you can be sure you're getting the exact same cells that I used in this test. If I was doing this project from scratch, I would use 314 amp hour cells. They're a better price per watt, and who doesn't want more capacity? Using my link will automatically populate a 5% discount at checkout, and you can get them even cheaper if you have them shipped directly from China. The only fee is a $30 fee for ACH, or a percentage of the total order if you use PayPal. ACH is probably the better deal, especially if you're ordering a lot of batteries. I have the discounts, comparison sheets, and spec sheets for all the batteries that I showed in the video today posted on my website, projectswithdave.com. Now that you have some battery options, what inverter should you use? The BougeRV that we used in the test today is really cheap because they're offering a 40% discount for my viewers for a few more days. Or maybe you should go with the Renogy, the most popular inverter on Amazon. But are either of these really the right inverter for your project? Watch this video where I check the performance of 7 2000 watt inverters and compare them head to head. That will help you decide which inverter works for you. Then watch this video on why you shouldn't build a 12 volt system. Well, I hope you learned something today. And remember, if the women don't find you handsome, they should at least find you handy. Thanks for watching, and I'll see you next time.